All right. So today I'm going to be presenting the hard work of my graduate student, Tianyu Chen, who'll be finishing up here soon. He couldn't make it because of visa issues. He's here in spirit. Okay, so what we're talking about today is trying to do a gradual approach to information flow control. So we're wanting the programmer to be able to decide what parts of their program do they want runtime enforcement of the flow control and what parts do they want static flow control. And there was some prior work that had a negative result that said you really can't do this. You can't have really gradual approach and IFC and like non-interference. Okay, so like if you want gradual languages should satisfy something called the gradual guarantee. And of course, the IFC language should satisfy non-interference. And they showed a counterexample in their design that you couldn't have both. So what we're doing here is showing, yes, you can have both. You have to be, there's some sort of subtle little changes to the language design to get that. Okay, so I'm going to kind of do a quick reminder on how the dynamic and static enforcement works with IFC. So I'm sure for many of you this is easy stuff. So like in this example, we've got some private input coming in, and then we're trying to publish it publicly. Okay, so this is bad. And if you've got dynamic IFC enforcement, of course you'll get a runtime error on this program, right? And what's going to happen is when you try to publish, it's going to look at the value that's coming through and look at a security label on that value and be like, okay, this thing is a high security value. We're not going to publish it. Okay, and so let's kind of this is going to become important later. And so like, where do these values get their labels from? Okay, there might be some primitive operations like this primitive input. You might have literals in your program that the programmer has annotated as being high or low security. And in some systems, dynamic information flow systems, you could get the security level from the execution context and use that for your value that you're creating. Okay. Okay. Over on the static enforcement side, you can see now I've annotated the types with their security levels. And of course, when you try to call flip here, it's saying I want a low security Boolean, but we're giving it a high security Boolean, and you're going to get a type error at that point. Okay, so that's those are the obvious sort of explicit flow cases. Okay, then of course you've got your implicit flow where maybe you've got some control flow that's impacting what's going on. So in this case, again, we've got a high security Boolean going into flip, and then we're using it in a conditional branch, right? And so the dynamic mechanisms of dynamic IFC they're gonna know to sort of infect whichever result from this branch with like the high security tag, and then when you try to publish that, again, it's gonna fail, okay, thanks to these runtime mechanisms, okay? Over on the static side, the type systems for static IFC are also smart about dealing with branching, and what's going to happen there is that the type system is going to see that, oh, we're branching on something that's a high security Boolean. Okay, so when I type check the branches, I'm going to know that those return values are high security, and you can't convert that to a low security. So again, here we're going to have a nice type error to say you can't do that. Okay. Then to mix in a little bit more complexity, these counterexamples require sort of a combination of all these language features. We also have to worry about mutable pointers. So in this case, okay, now we're back to dynamic enforcement. We're creating a low security pointer, okay, and then we're branching on some high security value, and then trying to write to the low security pointer. Okay, so this could be bad. You could be leaking something here, but the dynamic enforcement mechanisms, there's this non-sensitive upgrade mechanism that when you try to do that right to the pointer, it's going to say, hey, wait a minute, we're in a high security context. You're trying to write to a low security pointer. We're not going to allow that to happen. Okay, so this will again fail at runtime. And then on the static checking side, there's sort of a similar kind of static check that would happen. That, okay, here again, we're, in the branch, we're trying to write to a low security pointer, but the static type system knows that we're in a high security branch and will disallow that also at compile time. Okay, so that's sort of the standard static and dynamic IFC. Okay, now what if we go gradual? Okay, so what does that mean? So now we have this unknown security label, the star, okay, kind of like a wild card. And so here, the Boolean to flip there, we're saying we're not committing to whether it's high or low security. And when that happens, it means we're not going to do static IFC. We're going to do dynamic IFC for that sort of four things related to that variable B. Okay, and so for the branch here, we don't really know whether it's going to be a higher or low security branch. So we're going to use the runtime IFC mechanisms to deal with that. And so then what will happen is that at runtime, we'll know that it's high security. It's then going to be trying to cast a high security Boolean to bool of low, which is the return type. And at that point, that cast is going to trigger a runtime error. Okay, so this will error at runtime, sort of at the moment where you're going from, you've got a value that doesn't match the type annotation that's expected. Okay, so that's sort of a little taste of gradual information flow control. So now let's get a little bit into these properties that you want to have. I think I'm going to skip over what non-interference means in this audience, but explain the gradual guarantee. So what the gradual guarantee says is, okay, let's say you've got different versions of the same program where we're just changing in, some of the security labels on our types. Like we might be replacing a high security with star or low security with star. So we're just adding and removing stars, okay? So we've got this lattice of like how precise are the security types, right? And so star is like the least precise, and then bool and high are incomparable, but they're maximally precise. Okay, so the gradual guarantee says that in the absence of errors, when you're adding and removing security annotations, that's not going to change the behavior of your program. Okay, you're going to get the same answer out. You're not going to change from like computing 42 to 24 or something. Okay, so no crazy changes of behavior. Now, if you start thinking about errors, if you're adding security annotations, it might be that you add the wrong annotation, and so that could trigger either a compile time error or a runtime error. Okay, so that can happen. If you're removing security annotations, going from like high to star or from low to star, that should not change the behavior at all. Okay, and so this is the gradual guarantee. We use it sort of as a litmus test for lots of different gradual languages out there. Okay, so this prior work that I mentioned before by Eric Tanter and Matthias Toro, they developed a language called GSLRef, and so they came up with this counterexample where they had this program on the right that's more precise. That program runs just fine. Okay, there's sort of nothing wrong with that program. And then if you turn some of those high security labels into stars, the program on the left, it turns out, errors. Okay, and that violates the gradual guarantee. Okay, and the reason why it errors is that when you get to the assignment in the design of GSLRef, what they're doing is they're like saying, okay, we're in a high security branch, but we don't know the security level of the pointer. And if it turned out to be low, we'd be in trouble, and we'd be breaking non-interference. So we better conservatively make sure, treat it as if it's low. Okay, so they error on the assignment, okay, at runtime. Okay, but this breaks the gradual guarantee. But wait, okay, let's look again at the dynamic, the sort of less precise program here. GSLRef made the decision to allow the unknown security label as a label on values, which means that at runtime, you have values running around that have an unknown security label. this might seem sort of like a natural choice for a gradually typed language, but it turns out to actually be a slightly unusual choice, okay? So with gradual languages, you typically want to like mimic sort of both a dynamic and a static version of the language and just kind of connect those. And so if you look at like dynamic IFC languages, they don't have unknown as a runtime security label, okay? And then if you look at sort of just other gradually typed languages, not to do with IFC, we have unknown as a static entity, but we typically don't have unknown as a dynamic thing, okay? Usually you have all the information at runtime. Oh, this thing's an integer or this thing's a function. You're not unknown at runtime. Okay, so, and then the other kind of weird aspect of allowing unknown on values is that, the whole point of IFC is that your user is telling you like, oh, I've got some high security data, and that's an input to your system, and then your job is to protect that data, right? And so if they don't tell you what it is, what can you do about it, right? So it's a bit ill-posed. Okay, so that was GSLRef. And so they were saying, okay, we've got this, we can't get the gradual guarantee. They've got non-interference, but not the gradual guarantee. Then another paper came out about another system called GLIO. And what they did is they did two things. They changed two aspects of their language. They changed the way casts work so that, like, let's say you cast a low security value to high security. In GSLRef, that would change the label on the value. But with GLIO, they said, no, if you don't change the label, you let it stay as a low on that value, then they made that change, then you get the gradual guarantee. Though it's kind of interesting, they also made another change, which is they got rid of the star as a runtime security level. So they sort of made two changes to their language, and they claimed that the type-based reasoning one, the thing about cast, was what gave them the gradual guarantee. But when we saw that, we were like, when you change two things in an experiment, what about the other one? Okay. Then there was another paper, WildG, where what they did is they said, okay, we're not going to do this non-sensitive upgrade checking on assignments. We're going to go with a more restrictive static analysis. And it turns out with that approach, you can also get the gradual guarantee. And so what we came along and said, well, hey, wait a minute. Let's focus on that last column. And if we were to just get rid of the unknown label as a runtime label, would that get us the gradual guarantee back? And then we could keep our, the casts working the way we want them to, allowing us to do type-based reasoning. And we can keep the NSU checking as usual. And so our short answer is, the too long didn't read, is yes. If you get rid of unknown as a runtime label, you can get back the gradual guarantee. Okay. So of course, we had to verify that that was the case. So we designed a calculus very close to the GSLRef calculus. It's got mutable references, first-class functions, and conditionals. The semantics is sort of how we normally do semantics for gradually typed languages, which is you do a compilation to a cast calculus that has explicit casts in it. And in an IFC language, you also have all kinds of stuff in your IR for the mechanisms of doing the dynamic checking for like implicit flow and things like that. And then the thing that's a little bit unusual or new for an IFC system is that we use a coercion calculus to it's this little combinator language for expressing how to cast from one type to another. And so, and part of that language is another set of sort of coercion calculus that just operates on security labels, okay? And the reason why we're trying to go towards using coercions is that if you want space efficiency at runtime, then you need to be able, you kind of want to use coercions because they can be compressed. And so long sequences of them can always collapse down to just a few coercions. So this is sort of a stepping stone towards having an efficient implementation. So what do we prove? We prove the gradual guarantee. So that says if you have basically two versions of the same program. One is more precise than the other. If the more precise one runs to a value, then the less precise one should also run to a value. Okay, so it should behave the same. Okay, and then there's also the non-interference proof. Okay, which of course says that if you have some high security input, which we're just representing as a free variable here, and you've got maybe different values of high security inputs, your low security output shouldn't change, right? So no matter what, you're going to get the same public output. Okay, so we've proved that as well. Okay, so to sort of conclude, the non-interference property and the gradual guarantee property can coexist if we just make this subtle change of keeping those unknown labels out of the runtime security labels on values. Okay, we've done a AGDA mechanization of this calculus with a full proof of the gradual guarantee. We've got some but not all of the non-interference proof also mechanized. We do have a full non-interference proof for a slightly different language. Last year we had a different design that wasn't as good as this one, and but we had a full proof of that, and now we're still sort of updating that proof to match the new design. And then also, if you're interested in gradual typing and using coercions, then one nice thing about our development is that we show how do you do IFC using coercions. And with that, I will take questions.
Interesting talk. A very general question on this. So you usually have the problem that if you do not quantify information flow, you get a very high number of, let's say, technically correct but super uninteresting leaks. Like, is the password the one that I'm supposed to type in? Yes. Oh, that's a leak of my password. No, it's a normal login. So have you checked whether you can maybe quantify your approach so that you know how much is leaked? I mean, I can always check if the first character of my password is an A, then write something. If it is a B, write something. Then I leak the entire password, which is a completely different story.
So we have not looked at that at all. I think that's a great question. I guess maybe my question to the community is sort of how much of this sort of gradual typing story is sort of orthogonal to other aspects of information flow. You know, and sometimes they might be very orthogonal, so it might be easy to add that kind of quantification, and then other times you end up finding, sort of conflicts like what we did here with the gradual guarantee. So yeah.
I was just asking that because we have looked into the into information flow as a generalized property of what you usually do as a data flow for like Android applications, Java applications. Then you just get tons of findings that are technically correct, but if you find that to developers, they'll just ask, what are you talking about?
Okay, like, so from a practical rollout standpoint,
right.
Like you need to...
You're not leaking the password by telling you, hey, your login was correct. I mean, you have to show this somehow.
Right. Yeah.
Thank you.
Thank you for your talk. I was wondering, does your language support algebraic data types?
This calculus does not do algebraic data types. No.
Do you think it would be able, this approach would be able to support them?
I don't see why not. That seems like it would be a straightforward thing. I mean, usually like dealing with like mutable references is like the much more difficult.
Right. I was wondering because like let's say that you have like an unknown type and inside, and this is like an algebraic data type, and like the fields of this or the like elements inside these algebraic data types need a label in this type of fine-grained calculus. So that's why I was wondering.
Yeah, I mean, I guess like, are you thinking algebraic data type in a mutable setting or an immutable? So if it's mutable, then you're going to have all the same problems as mutable references. If it's immutable, I would think that there aren't really many issues.
So
there.
You should be able. Okay, cool.
Yeah.
Thank you.
Yeah.
Hey, so I actually don't have much background in this, but I had this question, like, does this like guard against side channel attacks? Like if
No.
there is, okay.
No.
And
At least I'm pretty sure no.
okay. And the implementation of this is like, is it done in the compiler or it's something on like something like a pre-processing step before you compile some program?
You could do that. Well, there's going to be a runtime component of this, right? So, I mean, you could do a lot of stuff in the compiler, but then at some point you're going to be generating code that's going to also, be doing runtime checking of things.
Okay.
And that you could have, your runtime could be in a library, or, you could be open coding it, and there's all the usual trade-offs, but.
Okay, so it's like some sort of like how smart pointers are there in C++. Like it tracks the ownership and deletes the ownership.
Yeah, yeah, I think
Okay,
that's
thank you.
roughly, yeah.
Thanks for a nice talk. So this might be
I liked your talk too earlier today.
Thanks. Perhaps my question might be also now to gradual security, but I'm curious about this approach could be scaled to the more complex control flows, like exception handling or first-class continuations, like call CC, effect handlers, and so on.
Whew. I don't know. I mean, I guess my question, I would immediately look to, is there dynamic IFC systems out there so far that deal with those kinds of control flow issues?
Okay, so designing the dynamic control flow for such a more complex control flow would be the first starting point.
If there isn't already literature out there on that. I mean, usually when I'm sort of tackling gradual typing stuff, the hard stuff tends to be on the dynamic side, and then at the crossover points, and so yeah. But I think that's a very, very interesting question, though, how to deal with like continuations or delimited continuations.
Thanks.
Yeah.
Thanks for the great talk, and let's thank the speaker again.